Hello and welcome to Chemistry with Dr. Clark. In this video, I'd like to talk about common ion effect. This is the second video in a two-part series talking about common ion effect. In the first video, I do talk a bit about the theory behind it and how it's related to Le Chatelier's principle. So if you do want to have a bit of a background in the problems, you should probably pause this video and go back and watch part 1 if you haven't already done so. If you're just looking to be able to do the calculations related to common ion effect, then you're in the right place. So with common ion effect, you're basically talking about two compounds. The first one really doesn't like to dissolve in water. So you have a container of water, you have a compound that you've thrown in, and for the most part, it will just sink to the bottom and sit there as a solid. But a very small amount of it will break up or dissociate. So you will get a small amount of this solid dissolved. And then what you're going to do is you're going to add a second compound. Now, the thing is, the second compound has something in common with the first one. They'll either both have the same cation or they'll both have the same anion. And the minute that you throw a second compound in with a common ion, you are going to decrease the amount of that first compound that can dissolve. Okay, there is a decrease in the solubility of the original ionic compound. And in these problems, what we want to calculate is exactly how much of that original low solubility compound can we dissolve if there's a common ion floating around. Okay, that's the problem that we'd like to be able to address. Now, the easiest way to do this is by looking at some examples. So if we look at this particular one here, it asks us to calculate the molar solubility of zinc sulfide. It does give me a KSP value in a 0.1 mole per liter solution of zinc nitrate. Now, there are a variety of KSP related problems. How do you identify this as a common ion effect problem? This problem is one of the very few that will give you two compounds. It's telling you about zinc sulfide, and it's also telling you about zinc nitrate. The majority of the problems will only deal with a single compound, right? It's rare to have two, and that's the first way that you can tell that this is a common ion effect problem. The other way is that when you look at the two compounds, there should be something in common, right? You've got zinc sulfide, which has zinc, but you've also got zinc nitrate, which also has zinc, right? If you want a common ion effect problem, you have to have something in common. Now, once you realize that this is a common ion effect problem, then the steps become very routine, okay? We're going to write the equilibrium first, then we're going to write the equilibrium expression, then we're going to build an ICE table, and then we're going to do the actual calculation. Now, I am going to go through these steps relatively quickly. If you find that you need a little bit more explanation or a little bit more practice, I have another video series that's related. It's a 3-part series that talks about calculating with KSP. So I've attached those, or I've put those in the description below, so that way you can just click on them and take a look. So if you do find that these are going a little quickly for you, you might want to pause it and go back and take a look at some of the easier, earlier problems that involve just KSP. Okay, so for this problem here, my first step is to write my equilibrium. Now you have two compounds, only one of them will form an equilibrium. The way that you can tell which one is the important chemical, the one that's going to form the equilibrium, is that that's the chemical that has the KSP. In this problem, I tell you that zinc sulfide has a KSP, and that's telling you that this is the important chemical. This is the one that's not going to dissolve very well. This is the one that's going to have the equilibrium. So let's start there. If I write down my zinc sulfide, it is a solid. The minute I throw it in water, it doesn't like water, but a small amount of it will dissociate or split up. So I'm going to end up with zincs, and I'm going to end up with sulfides. Now, the minute that they dissociate in water, they become aqueous. So that's an aqueous, and that's an aqueous. And to finish this equilibrium, there are two things that I need to do. First, I have to make sure that it's balanced, and second, I have to add the charges. because while they're together, the charges cancel themselves out. That's why there's no charges on a zinc sulfide. But once they separate, there's no cancellation of charges, so you have to tell me what they are. Okay, so let's balance first. I started off with 1 zinc, and I end it with 1 zinc. I started with 1 sulfur, I have ended with 1 sulfur. So it turns out that this thing is already balanced. It's 1 to 1 to 1. I did purposefully use an example here at the beginning. That's a nice, easy 1 to 1 to 1, just to make the problem look a little bit cleaner as a first example. In the next example, though, the balancing will require numbers other than 1 and 1 and 1. Now let's talk charges. If you remember, sulfur is in group 6 on your periodic table, and anything in group 6 on your periodic table has a charge of -2. Your zinc is a transition metal, and usually transition metals have more than 1 charge. But zinc is a bit of an odd one. So if you go to your transition metals, there's only 2 elements that don't have multiple charges, and zinc is one of them. Zinc can only have a charge of 2+. Now, that is an exception, right? Most transition metals do have more than 1 charge, and zinc does tend to show up in this type of problem a lot. So it is worth your while to memorize that zinc, when it forms an ion, always has a +2 charge. Okay, that's my equilibrium. Now what I'd like to do is write my equilibrium expression. So I'm going to say KSP equals products over reactants. Now you will notice that I have given a bit of space here. This is where I'm going to make my ice table, right? I wanted to leave a little bit of space under my equation to do that. So if we do our KSP, products on the top, reactants on the bottom. My first product is a zinc 2+. I put square brackets around it to show that it's concentration. And because when I balanced it, there was only 1 zinc, this gets a power of 1. My second product is going to be sulfur 2-. Again, we put square brackets around it to show concentration. And again, I used the 1 to balance the equation, so this will be a power of 1. Now, normally when you're doing equilibrium expressions, products go on the top and reactants go on the bottom. But when I look at my reactant is a solid. And if you have a pure solid or a pure liquid, you leave them out of your equilibrium expression. So although this zinc sulfide really should be here in the denominator, because it's a solid, I get to leave it out. So this is my KSP expression. And when you do KSPs, this happens all the time. Your denominator will always be left out because your reactant is always a solid. Okay, let's talk about our ice table. I'm going to build my ice table right underneath my equation. Each of the products get a column. So 2 columns because there's 2 products. And the whole thing should have 3 rows. So row, row, and a row. There we go. Now the reason why we do call this an ice table is because the first row is labeled with an I, second row is labeled with C, and the third row is labeled with an E. I stands for initial. This is how much zinc and sulfide you have initially. The C stands for change, because once you throw it in water, some of it will dissolve, so there will be a change in how much is dissolved. And if you give it enough time, eventually the maximum amount will dissolve and you will reach equilibrium. And equilibrium is a bit of a long word, so we tend to abbreviate it, EQLBM, equilibrium. Again, if you go back to the KSP series that I've linked in the description, it does talk about writing equilibriums, it does talk about writing equilibrium expressions, and it does talk about writing ice tables in detail. Okay, so you may want to go back there if you're feeling this is going a little quickly. Okay, now normally in those videos, the initials would both be zeros. Because initially, if you have given this thing no time, right? You put the zinc sulfide in water, and then you gave it exactly 0 seconds to split up. If you've given it exactly 0 seconds to split up, well then you would have 0 of this and 0 of this, because you've given it no time to split up. So initially, at time equals 0, we'd have 0 of the zinc, and we'd have 0 of the sulfide. But in this problem, you've got some pre-existing chemical. Because what you're doing is you're taking this and throwing it into a solution that already has zinc nitrate. So the amount of zinc that's originally in the problem is not going to be 0. Right? In the beginning, you do have no sulfide, right? Because there is no second source of sulfide. The only sulfide is going to come from the zinc sulfide, right? It'll happen when your zinc sulfide dissociates. And if you've given it absolutely no time to dissociate, then none of it has dissociated, and so you have 0. But the zinc is coming from 2 different places. Some of it is coming from this equation, but some of it is also coming from the original zinc nitrate. And I need to take that into account. So my initial here is not going to be 0. That is very different from the 3-part series that I've mentioned about KSPs. Okay, this here is the big difference. Now, in order to address this, what we're going to do is we're going to talk about this chemical over here on this side. So my second chemical is zinc nitrate. There we go. Now, the cool thing about this is that while this compound hates water and really doesn't want to dissolve, this compound loves water. You put it in water and it will 100% break up. So I don't use an equilibrium arrow, I use just a regular arrow. Because this stuff is going to break up 100% and none of it is ever coming back together. So again, if we break it up into its ions, it's zincs and nitrates. So you will get zincs and you will get nitrates. Once they broke up, they're both aqueous. You do need to balance. So I've got 1 zinc versus 1 zinc. Perfect. I have 2 nitrates, right? It's NO3 with a 2 after the bracket. Tells me I've got 2 of them, so it's 2 nitrates. And I do need the charges. If you look up nitrate on your polyatomic ions table, it's going to be a -1. And we've already talked about why zinc would be a 2+. Now for this one here, you initially started out with 0.1 moles per liter of zinc nitrate. So 0.10 moles per liter. But now that's going to completely break up. In the end, you're not going to have any of this. So what is it going to break up to give you? It's going to break up to give you your zinc 2+ and your 2 nitrates. So it's going to break up to give you, well, for every one of these, you get 1 zinc. So if you started with 0.1, you should get 0.1 of these moles per liter. And for every one of these, you get 2 nitrates. You get twice as much. So 1 zinc nitrate gives you 2 nitrates. So if you started with 0.1, it will give you 0.2 moles per liter. Now, really, the nitrate I don't care about, because is the nitrate part of the equilibrium that I'm focused on? No. What's part of the equilibrium I'm focused on is the zinc. So for every 1 zinc nitrate, you get 1 zinc. So for every 0.1, you would get 0.1. Right? So for the zinc, this is how much I already had sitting in the beaker before I ever attempted to add the zinc sulfide. This is the initial. Now, part of the reason why we did want to talk about the 1 to 2, even though the nitrate is not important, is because sometimes the important chemical does have to get multiplied. Right? For this one, for every 1 zinc nitrate, you got 2 nitrates. Right? So if you started with 0.1, I had to double it to figure out how much nitrate I had. And sometimes the important chemical will end up being a 1 to 2, so you'll have to double it. Or a 1 to 3, so you would have to triple it, right? Okay, so you now know how much of this that you started with. You started with 0.10. Now you will notice that my table is a little bit cramped. So the units here should be moles per liter. But we can compress that. Because we use moles per liter so often, we have a shorter form. It's a capital M, and it's just pronounced as molar. So this would be 0.1 molar, or 0.1 moles per liter. Okay, it's just an alternate symbol and an alternate way of saying it. So if you wanted to, you could just call this 0.1 molar. Okay, now this is different from the previous series that I had on KSPs, because in the previous series, there was no second chemical, right? This is new to this type of problem. So in the earlier ones, these would have both been zeros. Okay, but now the next step will be the same as any other KSP problem. Once you've put this in the water and you give it some time, some of it will break up. There will be a change. How much breaks up? I don't know. That's what I'm looking for. So I have to give it some sort of variable. If you were in math class, you'd just call them x's. But because you're in chemistry and because we're looking for solubility, we're going to call it S. How much does it change by? It changes by S. Now it is going to be an increase, right? Because a little bit of this will break up, so it will be plus and plus. And one of the important things here is that these coefficients used to balance come into play here. This is a 1-to-1 relationship, so this is going to be a 1-to-1 relationship. In one of the later examples, I have like a 2-to-1, so it would be a 2s to a 1s. Now you just do your math. If I have 0 and I'm adding 1s to it, 0 plus 1s is s. If I have 0.1 and I add s to it, this would be 0.1 plus s. Think of it in terms of math, right? If you were in math class and I said, what is 2 plus 1x? Well, that would be just 2 plus x, right? Because the 2 is a number, the x is a variable, and you can't put them together. Here, the 0.1 is a number, and the s is a variable, and you can't put them together. Okay, now at this point, once you have your equilibrium, once you have your equilibrium expression, and once you have your ice table, normally we take the values from the equilibrium and just substitute them in, and then do our math to solve it out. Now, if we attempt to do that here, okay, again, let's just do a demonstration. If I were to put these two numbers in, if I were to take this one and put it here for the zinc, right, because this is the zinc number, and if I were to take this one and put in for the sulfur, because this is the sulfur number, I'd have KSP equals 0.1, plus S times S. Now, you know in the world of math that if you have a binomial times a monomial, you're going to have to do distributive, right? This S is going to multiply by the 10, and the S is going to multiply by the S. So you're going to have KSP equals 0.10S plus S squared. Now, this problem does give you the value of K. So if I were to put in the value of K, 2.5 times 10 to the minus 22 equals 0.10S plus S squared, what I've created is basically a quadratic equation, right? If I switch these two around so that way the S squared is first and the S is second, and I move my constant over, I would get 0 equals S squared plus 0.1S minus 2.5 times 10 to the minus 22. So in order to solve for S, you would have to haul out your quadratic equation. Now for some of these, you're going to get cubic S's or you'll get quartics, S to the power of 3 or S to the power of 4. And they become a lot harder to solve mathematically. Now, if you are required to do that, then you're just going to have to work your way through the math, and that's just the way life is. But for the most part, we're chemists. If we're talking about this problem here, every number in this problem has a small amount of error associated with it. Like when I say the concentration of the zinc nitrate is 0.1, what I really mean, it's 0.10 plus or minus a little bit, right? Because there's an error here. When I measured the volume that I put the zinc nitrate in, right, there's a little bit of error there. If you've ever used a beaker or a graduated cylinder or any piece of glassware, you know that when you line up the liquid with the mark, there is a little bit of uncertainty, right? So there are errors going to be in every number that we have here. So as chemists, what we've decided is, if I can make an approximation or an assumption here that makes the math a lot easier, but it doesn't really mess with my answer too much, then we've decided we're going to go with it, okay? So what we'll do is we'll make an assumption. It will make the math a lot easier, and the answer that we get will not be the correct one, but it will be so close that we will consider it to be within error. Right? In chemistry, because we make so many measurements and all the measurements have errors involved in them, we don't mind if the math also introduces a tiny amount of error, because that's the world we live in, right? Everything we measure, you measure a mass on a scale, there's a plus or minus a little bit. You measure a volume in a beaker, there's plus or minus a little bit. Everything we do has a certain amount of error. So because these two original numbers have a certain amount of error, then my final answer already has a small amount of error. Right? If I throw in a little bit more error by making an approximation, I'm willing to accept that. Now, the approximation that we are going to make, we are going to say that this zinc sulfide doesn't like to dissolve. So its solubility is going to be very, very low. Okay, it does not like to dissolve, so the solubility is low. I've already said that common ion effect makes it even lower. Okay, so it didn't dissolve very well, and now it's going to dissolve even worse. So this value of S is going to be very, very tiny, okay, compared to this number. It's like if you had $1 million. Okay, so you have $1 million in your pocket, and you're walking down the road, and you find another dollar. So you put $1 in your pocket. You now have $1,000,001. So if someone asks you, hey, how much money do you have? Would you say I have $1,000,001? Or would you just say, hey, I got $1 million? Right? You'd probably round it off to the million because the 1 is so tiny in comparison. And that's what we're going to do here. We are going to say that this S is so tiny in comparison to the 0.1 that we can ignore it. Right? This would be like saying I have $1 million plus $1 extra dollar. Right? The 0.1 looks small, but the S is so much smaller. So for this one here, we're going to make a bit of an assumption. We are going to assume that the S is much, much smaller than 0.1. Okay, we'll actually use 2 less than signs to show that it is ridiculously small. So if we assume that, then I can say that 0.1 plus S is approximately 0.1. Okay, and the 2 little squiggle signs, that means approximately. So what we can do then is when we substitute in, instead of saying that the amount of zinc is 0.1 plus S, I can say that the amount of zinc is just 0.1. Now, this over here is still just S. So how much sulfur do you have? I have S. So my KSP equals 0.1 times S. This is much, much nicer than ending up with a quadratic equation, right? Because here I had 0.1 times S and I had an S squared. For this one, I just have the 0.1 times S. It makes life a lot easier. Okay, so for this problem here, you will have to make a little bit of an assumption that goes with the common ion. Now to finish it, you're going to pull down your value of KSP and you're going to solve for S. S is the solubility. So my KSP is 2.5 times 10 to the minus 22 equals 0.10 times the S. If you want the S by itself, I'll divide this by 0.1 and I'll divide this by 0.1. So if we pull out our calculator, 2.5 times 10 to the power of 22 negative divided by 0.1 gives me 2.5 times 10 to the minus 21 equals S. Now S does stand for solubility. This is the molar solubility that you're looking for. And because it's a solubility, you have to give me the right units. And the units for solubility would be moles per liter. Or just molar, right? That'll work as well. Now at this point, we should probably reevaluate our assumption. I assumed that whatever the value of S was is going to be smaller than 0.1. Is 2.5 times 10 to the minus 21 smaller than 0.1? Yes, it's really small, right? This is 0.25 20 zeros, and then a 2.5. That is so much smaller than the 0.1 that this is an excellent approximation. It saves us a whole lot of work, and if you were to actually throw this in the quadratic formula and work out your answer would be this, because the amount of error that this introduces is so tiny that if you round it off to just like 2 significant figures, you don't even see it. If you actually wrote out the first like 5 or 6 decimal places, I'm willing to bet that this approximated answer and the real answer would still be exactly the same, right? Because this is such a small number in comparison, the error is going to be very, very tiny. But it does make my math life a whole lot easier. All right, so let's try another one. Okay, so I would like to calculate the molar solubility of silver carbonate, and I do give the KSP, in a 0.02 moles per liter solution of sodium carbonate. Now, we're going to follow the same steps we always do. Write the equilibrium expression, write the ice table, and then do the calculation. So between these two chemicals, you can see that there are 2. You can see that they both have a carbonate. So this is definitely a common ion effect problem, okay? 2 compounds and they share something in common. This is the only one of the 2 that has a K value, right? Sodium carbonate doesn't have any KSP. The silver carbonate does have a KSP. That makes this the most important chemical, which means the equilibrium goes with this one. So that'll be Ag2CO3 solid in equilibrium. When you put it in water, a small amount will dissociate, so you will get some free silvers, and you will get some free carbonates. The minute they dissociate, they do become aqueous. So aqueous and aqueous. The 2 things you need to do is balance and tell me the charges. So for this one here, you started off with 2 silvers, right? It's Ag2. Because there's 2 silvers, that puts a 2 here. There is only 1 carbonate, right? CO3 is a unit. There's only 1 of them here. There's only 1 of them there. So you just need 1. That's perfect. Now, if we do charges, carbonate is a polyatomic ion. So if you take a look at your table of polyatomic ions, this has a charge of 2-. Now, your silver is a transition metal. But just like the zinc, the silver is an exception. It doesn't have more than 1 possible charge on it. So for the silver, there's only 1 possible charge, and you should memorize it because silver is one of our favorite elements for this kind of problem. Silvers have a 1+ charge. Okay, the only 2 exceptions in the transition metal are silver and zinc, and they both showed up in this video. Zinc is always 2+, and silver is always 1+. Okay. Now, I am going to build an ice table here, so I'm going to skip some space to come down to my KSP. KSP is products over reactants, but my reactant is a solid, so I get to leave it out. So I really am just worried about products. My first product is a silver 1+, square brackets to show concentration, and I use the 2 to balance the equation, so I'm going to put a 2 here. The second product is a CO3, 2-. Put square brackets around it to show that it's concentration. And I use the 1 to balance it, so I'll put a 1 here. And like I said, the reactant should go in the denominator, but the reactant is a solid, so I leave it out. Then we build ourselves an ice table. The ice table has 1 column for every product, so 2 products, 2 columns, and it does have 3 rows. There we go. Initial, change, equilibrium. Now, if we talk about initially, this is time equals 0. The silver carbonate has had no time to break up. So you're not going to get any silver or any carbonate from the silver carbonate. Okay? None from this. But you do have a secondary source. In this water, you've already got some sodium carbonate. So where's the only place you're going to get silver? The only place you're going to get silver is from the silver carbonate. right? That's the only source. So if you give it 0 seconds to break up, that gives you 0. But the carbonate is coming from two different places. It's coming from the silver carbonate, but it's also coming from the sodium carbonate. Now, this here has not had a chance to break up. So in the beginning, you have none of it. So none from this source. But this sodium carbonate was pre-dissolved. The sodium carbonate was already in the water. So whatever amount of carbonate you have from the sodium carbonate, that's what you have initially. Like the last time, I'm going to write a second equation. This was an equilibrium because the silver carbonate doesn't like to dissolve, so it is an equilibrium. But the sodium carbonate loves to dissolve. Okay, the second chemical will always love to dissolve. So the minute you put it in water, it's going to 100% break up. If you've got a sodium carbonate, that's going to give you some sodiums, and it's going to give you some carbonates. Just like over here, you have to balance it, and you have to show me the charges. Okay, so this is aqueous, this is aqueous. If we try to balance, I started off with 2 sodiums, so I'll need 2 sodiums. I started off with 1 carbonate, so I'll need 1 carbonate. Now it's balanced. If you look up carbonate on your polyatomic ions, which we already did, you can see that its charge is a 2-. And if you look up sodium on your periodic table, sodium is in column number 1, so it has a charge of +1. Now this problem tells me that I started with 0.02 moles per liter of sodium carbonate. 0.020 molar. Let's use the capital M rather than the moles per liter because I don't have a lot of space. So when this thing breaks up, for every 1 sodium carbonate, I get 2 sodiums. I get twice as much, right? For every one of these, I get 2 sodiums. So here, I'm going to get 2 times 0.020. So for the sodium, I'm going to get 0.040 molar. Now, in the end, am I worried about sodium? No. Because does sodium show up in my ice table? No. So even though it's here, even though we talked about it, the sodium really isn't going to take part, right? It's not part of our ice table. Let's talk about the carbonate. For every 1 sodium carbonate you break up, you get 1 carbonate. So if you broke up 0.02, you'll get 0.02 molar. And this is the amount of carbonate that's already sitting in the water at the beginning of the experiment. So this is going to be my initial carbonate. The last time we had a common ion that was an anion. This time our common ion is going to be the anion. So that's how much you have at the beginning, 0.020 molar. Just like the last time, you're going to give this a little bit of time to break up. When it breaks up, you'll get some extra silver, so plus S. You'll get some extra carbonate, so plus S. And you have to keep in mind the numbers used to balance it. Because for every one of these that breaks up, you're going to get 2 silvers and 1 carbonate. You're going to get twice as much silver as the carbonate. Okay, so 0 plus 2S would be 2S. 0.02 plus 1S is 0.02 plus 1S. Maybe my table should have been a bit bigger. Now again, we're going to make a little bit of an approximation. We are going to assume that the S is so much smaller than the 0.020. Now I realize that 0.020 is tiny, right? That's a small number. But what I'm going to assume is that the plus 1S is even smaller. It's so much tinier. Because that will allow me to say that 0.020 plus 1S is approximately 0.020, right? It basically allows me to get rid of the 1S. Because when I substitute them in, this will make my problem so much nicer. Okay, so let's substitute them in. How much silver do you have? I have this much silver. So I have 2S. Don't forget that it was squared. And what you're going to find is that the number in front of the S and the power are the same, right? because this silver was balanced using a 2. And that 2 shows up in the ice table, but that 2 also shows up here as a power. So it'll be 2s squared. How much carbonate do you have? I have 0.020 to the power of 1. Now again, I technically have a little tiny bit more than that, right? I have 0.020 plus a little bit. But that little bit is so tiny that I've decided to ignore it. For this problem, I did give you a value of KSP. So it is 8.2 times 10 to the minus 12. From here to the end now, this is just a math problem. Okay, so let's keep our 8.2 times 10 to the minus 12. If you have 2s squared, that means the squared belongs to both the 2 and the s. So that will give me 4s squared. And if you take anything and raise it to the power of 1, it doesn't change. So 0.020. Now I'm going to combine these two terms. If you've got 4s squared times 0.02, the 0.02 and the 4 will multiply. So that'll give me 8.2 times 10 to the minus 12. 4 times 0.02, that's 0.080 times s squared. Now if I want to solve this, I need to get the s by itself. So I got to get rid of the 0.08 and I got to get rid of the square. The first thing that you're going to do is get rid of the 0.08. The number that's multiplied in first, that's the number that you're going to get rid of. So 0.08 and divide by 0.08. All right, so if we pull out our calculator, I've got 8.2 to the power of 12 minus. So 8.2 times 10 to the power of minus 12. Divided by 0.08 will give me 1.025 times 10 to the minus 10. Those cancel out, so that's s squared. And if you have s squared and you'd like to get rid of the square, then you would have to take the square root of both sides. So if I take the square root of this, square root, I get an answer of 1.01 times 10 to the minus 5 equals s, which is my solubility. And remember, if you're looking for solubility, this would have units of moles per liter or just capital M for molars. Okay, now let's reevaluate our approximation. In our approximation, we said that the s was going to be way smaller than 0.02. In the first example, it was. It was very much smaller. Now this number is tiny, but it's not as tiny as the last problem, right? Basically, I've got 0.0000101 versus 0.020, right? If I write the value of s here, I can see that, yes, this value of s is much, much smaller than the 0.02, but it is much closer than it was in the last problem. So in the last problem, I probably would have had very, very small amount of difference between the right answer and my approximate answer. In this example, the difference is going to be a little bit more noticeable. So instead of 1.01, it might be 1.02. Okay, it's still going to be tiny, but not as tiny. Okay, this approximation only works if the s value that you get actually is much, much smaller than the number that you started off with the common ion. Okay, so I'm hoping that these problems have helped you if you're working on common ion effect problems. And my suggestion is stop the video, go back to where I just showed the problem, go through the solution on your own, and then rerun the video to see how your answer matches mine. Now, I cannot say it enough, practice is your friend here. The more of these that you do, the better that you'll get at them. The other thing that'll help you is organization. I write out my problem the same way every single time. Equilibrium, equilibrium expression, ice table, calculation. So that way, every single problem looks the same as every other problem, and it helps keep me from getting lost. So as always, I'd like to say thank you for joining me here at Chemistry with Dr. Clark.